Welcome to the final episode of T Cubed, our tea experiment. So let's have a look at our results so far. So from backwards to forwards, here we have first of all the measurement of the caffeine level. You can see the first two measurements is at 77 degrees. You can see 77 graph, 77 degrees centigrade. The first few measurements are a bit weird and flat. After that we have this peak here at nearly 275, which is the caffeine peak that we expect. If we look at 62, that's a lower temperature. We can see, looking at the numbers, for maybe 30 seconds here, the red curve, and 30 seconds here, the red curve, you can see that they're considerably lower. And if we look at the higher temperature, 85, we can see that they're higher. And we get more noise, but we also get out of this ugly bit very quickly. And the curve is at 275. If we look in our table of results, so this is the results for the peak height at 275, and we can see that it goes up and tails off over time, and that it's lower for 65 degrees than it is for 77 degrees, than it is for 85 degrees. And that not only is the final concentration that they're going to go to different, but also the rate. So that's not spectacularly surprising, but it's something. That's our data that we've measured. Then if we look at the other one, whoops, hang on. Where is it? Tea brownness. So if we look here, we can see this was our curve shape. You can see it cuts off. This is the whole tea. You can see at low concentration. So after 30 seconds, we can see the caffeine peak. But past that, the darkness, the blackness at this wavelength is so intense. The color absorption at this wavelength is so intense that we can't see anything, which is why we did the extraction in the first place, to be able to measure the caffeine. But we're measuring down here at 550. And we're actually averaging over a short range here to get a value for brownness. So I've calculated that here on this one called Calculating Average Brownness. Let me show you how I did it. So this is the data, the original data, and I've taken the points between 500 and 550, I believe. There we go, 500 and 550 nanometers, and that goes down in a curve, and those are the different times on this particular one. So this is 85, the other ones are below. Then I've taken those and I've divided them by the value at 600 seconds. So that is a curve and a curve that goes steeper, and I've divided them by the same wavelength at 600 seconds, which brings them all down to a much more similar value. Obviously, if we took the average of a curve, it would be distorted by the shape of the curve, and we would consider the high values much more than we consider the low values. So to avoid that mathematically, what I've done is I've divided them by the value at 600 seconds to normalize it already. That means that obviously this column, 600 seconds, is all 1 because it's it divided by itself. All of the others are less than 1 because they are divided by the value at 600 seconds. To make the curves all similar and come out different heights, I've used the same 600 second value, so it's the 600 second value at the highest temperature. That's 85 degrees. So that's the one that comes out at 1. All of the other values should come out less because we get less brownness at any other condition. Oops, sorry about that. So if we look at these, I've divided those values, all of these values, by the value at 600 seconds. You can see it changes slightly over the frame, but not very much. Maybe the 15-second one does, but all the other ones don't very much. Then I've taken the average. Mittelwert is average, so it's the average of all of those values between 500 and 550 nanometers, and put them into this table, and those are the ones that we've put into our normalized average brownness, which is, whoops, wherever it is here. This is the brownness index versus time curve, which is those data points that we just calculated. And as we can see, it's out of 1. The 62 degrees centigrade one comes out as the lowest brownness, the 77 comes out higher, the 85 comes out higher, and this 600 point is the one that we've used as our reference for 1. Our actual final value would be higher, but we never got there. What we can also see is that these curves are a bit weird, so it's a fairly curved piece of data. The odd points aren't on the curve, but that's not spectacularly surprising. It's a fairly random situation. The tea bags are swirling around, the temperature's changing, all kinds of things are difficult. So it is not surprising that we've measured a couple a bit low. That's not worrying. That's just part of the smoothing process. But what is interesting is that the first point at 30 seconds on all of the curves is high, and this curve does not go to 0. If it goes down to 0, it would be here, so it wouldn't be 0 time. Sorry, I just remembered you can't see the pointer. So if we extrapolate the curves to 0 brownness, it's not 0 time, it's about 10-15 seconds, something like that, really, which means that at low time something else happens. So I've removed those points. Whoops. I've removed those points to fit it. Where is my calculation? Here it is. So now I fit the data. So this is an example. This is the 77 degrees example. So I've taken all of the data points, but this one 30 seconds. So I've removed the 15 seconds one because that was flat. And obviously you can't fit a curve if you include something that's going weird. We'll have to think about what's happening. You will have to think about what's happening at that point. If we look here, we can see it's a fairly good curve. And I've taken the information for the curve, which is on our Moodle, but you can see it in this sheet. Here is the equation. So the equation is, I've taken an offset value, which is P92, so it's this one, A. And then I've taken an exponential value, so this is the pre-exponent, A, 90, and S, yeah, PQRS, so it's that one. There's a pre-exponent multiplied by the exponential of R, which is C here, multiplied by n minus q, which is, so n is the data point, that's the time, minus b. So what I've done is I've shifted it both in on this axis, on the time axis, by b, and I've shifted it on the vertical axis by p, which is that one, which is a. So I've shifted it in both axes, or allowed it to shift in both axes, because it obviously doesn't start from 0. And then we've got a standard exponential where we've got the exponential factor is this one, R is C, and we can see what the shape of the curve is from that. So I've fitted that same equation to all three, and we can see that they fit. Here is another one. So this is the 62 degrees. You can see that one fitting quite well. It's not a brilliant fit, but we know that from other papers that it is what one would expect. So that's good, because otherwise it would be extremely dubious to do this. So now I've fit it, sorry, I'm zooming around too much on here, But now I fit it to that, and then I stopped allowing them to change. So on the second fit, I didn't allow the pre-exponent d, which is the thing multiplied by it, and I didn't allow one of the other things. No, I didn't allow d to change. So that's good, because the less things that you change per run, the better, because they're all teabags in different temperatures. We expect the exponent to change, the rate of curvature to change, but the other things shouldn't change that much if they're to do with how the teabags are dumped into the liquid, the volume of the liquid, how it's stirred, and things like that. So if we can fit it with these, which I managed to do, that's good. Sorry, I keep not looking at you. So that will be those curves, and I've put them into this diagram, diagram 6. So this is the fitted curves, and we can see the shape of them in 3 dimensions. And where are we? Yeah, it took me a while to fit this. So then if we go back to the other one, whoops, if we go back to the caffeine one, and we superimpose those curves, which I did tell you on the Moodle site, but some of you are looking at this on the internet, so you won't know that. So what I've done here is I've multiplied the fits from the brownness curves by a number that is fixed at the end of the run, so either at 600 for 85 degrees C or at 900 for 62 degrees C. So I fit it on the last point. I forced it to go through there by dividing by that point, and I was looking to see whether the same shape curve would fit the caffeine as well, because that means that the factors that cause the offset, which we don't know, which I think I know, but that's your job to think about. The factors that cause the offset on time at the beginning are possibly the same if these curves fit each other, and they're a reasonable fit. It's not a super good fit, but you can see it goes through most of the points on most of the curves, and the ones that it doesn't go through are not in a smooth curve anyway. So it's not the worst fit, it's not the best fit, it's not the worst fit. I'm sorry about the axes, I couldn't get those to show. So this bottom axis is time in seconds, the vertical axis is both amount of absorption at 275 nanometers for the caffeine, and it's an altered normalized curve for the brownness to fit onto the caffeine curve. So that's why the vertical x-axis, the y-axis is not very easy to define, because I've fitted it. I've tried to fit the data curves from the brownness to match the caffeine curves. Because that happens to look good, it means that the shift is constant, which means that if we want to make a certain amount of brownness, or if we take this tea and we make it more concentrated and dilute it, we don't actually get any different. So if we make tea at 62 degrees for 90 minutes, 900 seconds, so 15 minutes, and we dilute it down to this concentration, we get the same result in terms of brownness and caffeine, not the same result in terms of other compounds maybe, but it's the same result in terms of brownness and caffeine as we would have done if we'd just done a shorter extraction. Obviously it would be less efficient in the amount of tea bags that we would need to do that, but we would get the same result, so we can't actually change the ratio of caffeine to bitterness by changing the time. What we can, however, do is change the ratio of caffeine to bitterness by changing the temperature, because you can see in this curve, or up here in this table where I actually calculated it, the numbers that they're multiplied by are not the same. So I had to multiply the brownness curve by more to get it to match the low temperature caffeine values than I did have to at the high temperature. So at 85 the multiplier is 2.436 and at 62 it's 2.84. It's not a massive difference, but it is a difference. So if we extracted it at even higher temperatures, we would get more out than if we extract it at lower temperatures, but it's the ratio between the caffeine and the tea, which I will let you try to extract yourself from this data, because that's the point of this exercise. Then we'll write it up, then you can have a look, then we'll discuss it. So the job for my students right now is to write up our experiment like a paper, and then we will publish it on our open access server, maybe somewhere else, so that we can see, so that other people can see that you do get more caffeine out at different temperatures, that the rate of extraction is fairly similar between caffeine and whatever the brown compounds are, polyphenolics, and that maybe we don't have so many possibilities to change the amount of caffeine in our tea as we hope we might, as we might have thought we did. Right, I'm going to stop there because, whoops, I've lost my thing. I'm going to stop there because I've opened too many windows and it's complicated enough. So I hope that's helpful. So again, this is the whole of the data on one graph. There's both the brownness data and the caffeine data, but the brownness data has been shifted. So it's better to look at the original two graphs, which would be, where is it? This one. This one here. And so that would be the caffeine amount going up over time. You can see they may be slightly more bent, more sort of have more of a corner than a smooth curve would. And the caffeine curves where it is in here, brownness index versus time. This is the actual data. These are just fit with the spline, so the line is artificially curved between the points. The points are the things that we actually measured. The curves are not. The fits are in the spreadsheets, which you can have, and you can fit them again if you want to. This is a 3D plot so that we can see it, but it doesn't show as much as I would like because we haven't got enough difference in temperature. So what I would be interested in is this axis here. This is the temperature axis going backwards, but because we've only got 3 measurements in temperature axis, and you can see it's pretty much linear, it's difficult to see what's going on. So if we were to do more measurements, they would be more temperatures. Okay, I'm going to stop. So write it up yourselves as students. Obviously, if you're just an outside viewer, wait till the students write it up and we will post that as the next thing. Then we'll have an live piece of research on, does caffeine and tea brownness, can you control it by changing the temperature and time that you extract your tea bags by? Okay, so goodbye. See you next time. Hope that I get plenty of data off the students, plenty of write-ups from the students, so that I can collate it all and put it on the internet for you.